now going to survey just a few of the brain imaging techniques that neuroscientists have at their disposal. We have a bewildering variety of very high-tech means of generating images or recordings from brains, but interpreting them turns out to be very, very difficult. As we'll see, our ability to create images far exceeds our ability to interpret those same images. We're going to just look at a very few of these, but crucially including both EEG, which is brainwaves, and fMRI, which is has captured the public imagination like no other scientific imaging technique. But we're going to begin with EEG, or recording of brainwaves. Now, you might not think of this as an imaging technique, but it is an imaging technique because what we're doing is using sensors to make information about what's going on in the brain visually available. In this case, they look like waves, multiple waves. It's the oldest of our brain imaging techniques. It goes back to 1924. And it's non-invasive, which means that you can do it on children, you can do it on sick people, it's no trouble. It's a little bit of a hassle to set up. You put on like a swimming cap, which is studded with electrodes, typically 128 electrodes, although numbers vary. And they record changes in electrical conductivity at the scalp. So it's non-invasive, using scalp electrodes, and its ability to monitor changes in the electrical conductivity at the scalp is very fine in time. It can record changes which go on maybe hundreds of times a second. So excellent temporal resolution. On the other hand, those recordings are being made on the scalp, and saying where that variation comes from, associating it with the brain at all, is very, very difficult. Now, it was Hans Berger who first did this in 1924, and there's a snapshot from the variation on the scalp that he recorded using a single electrode. You got to start somewhere. Now, there's two lines shown there. The lower line is a 50 hertz alternating current, which is present in the electrical signals in many houses, and is here used for reference. At the top, you can see variation as measured at the scalp electrode. Now, the first thing to note is that most of that variation is at the 50 hertz, so whatever the brain is providing is relatively little, but our ability to monitor these small fluctuations increase greatly. We're great at building technologies, and these days you can obtain 128 complex recordings that look, each one of which looks a bit like this, from an array over the scalp. Now, how do you interpret this? Well, these are desperately difficult to interpret. When you have a complex time-varying signal like this, one way that an engineer would approach this is to say, that signal is made up out of the sum of a bunch of simpler signals at different frequencies. Just like in your stereo, you have a graphic equalizer where you can selectively adjust the bass, the mid-range, and the treble. So a signal like this can be broken down into its low frequency, mid-frequency, high frequency components. Here's an example of that signal broken down into 4 of its components: low, medium low, high, and very high. And such frequency ranges are given names named after the Greek alphabet, but there's no alphabetic ordering to them. One simply has to learn the conventions, and there's a lot of conventions involved. And it's very, very difficult to say what these mean, but one thing we find, and this is a very important thing, is that there are changes in the relative intensity of these frequency bands that are associated with changes in states of consciousness. So the profile of these component frequencies would look different in a sleeping person than an awake person. That kind of correlation, something we know, states of consciousness, so this person is asleep, this person is awake, and something that changes as that happens. This is going to be clinically very useful. We don't necessarily understand where the signal is coming from. The brain is always endogenously active. The brain is always creating electrochemical variation. And what the EEG records is wholesale electrical activity diffusely spread. And its origin is largely from that part of the cortex that lies, by chance, close to the skull. So the neocortex, if you imagine it as a big sheet of tissue, has been crumpled up to fit it inside the skull. And when you crumple a sheet of paper, some parts, by chance, happen to be nearer the outside than others. So we're getting a really poor record of anything to do with the brain, but it does provide us with a recording which changes sensitively with time and which can be shown to vary as states of consciousness change. So the difference between dreaming and deep sleep, for example, is easy to spot. And the difference between being in a coma and being awake is easy to spot. Now, when the brain changes, along with some things that we have a passionate interest in, like coma, for example, we would very much like to understand coma, then we have potentially a useful clinical tool. This doesn't require delving into too many of the mysteries of theories of cognition. We have something that we're familiar with, states of consciousness, and something that co-varies with it, this mad signal recorded on the brain. Here's an example of an EEG trace showing, again, a clinical application. Here you can see the change in the waveform right at the time of the onset of an epileptic seizure. An epileptic seizure is an uncontrolled electrical discharge in the brain, and such a discharge is very easy to see on the EEG. Again, no big theory involved. We've got a medical condition that calls out for attention. We've got something on the brain we can record that co-varies with it. This is very, very important work. So a nice thing about clinical applications of EEG is that they don't depend, by and large, on your theory of mind. They don't depend on whether you prefer representational, Cartesian, embodied theories of cognition. They're developed pragmatically. The EEG record changes as the clinical presentation changes. Now, EEG is used in other ways as well. Non-clinical application of EEG is quite common within the field of cognitive psychology. Here, we don't have the same kind of security. That is, your interpretation of this fluctuation is wholly dependent on your theory of mind. And inevitably here, we're going to be talking about using the computational theory of mind. A common technique used is called the event-related potential, which involves subjecting some innocent subject to the same stimulus, the same thing, over and over and over and over again, and averaging the recordings over all these presentations to see what's left. And you end up with a trace like this, an event-related potential. Whether this can be meaningfully interpreted or not, whether this is a sane undertaking or not, depends entirely on your view with respect to computational theory of mind. So there's applications of EEG which do depend on your theory of mind, and there's applications of EEG which don't depend on your theory of mind. Those which don't are enormously useful in a clinical setting. Those which depend on your theory of mind lead to debate among experts within the bubble who all share a view and can be pretty much ignored by those outside the bubble.